This is our second video on heat and thermodynamics, and in this video we will explore the ideal gas law and ideal gas equation. I found this interesting picture and I thought that I'm going to use it to show you how the pressure changes when some conditions are changing. So I found this picture from Encyclopedia Britannica. In this picture you can see that when the volume is decreasing, but the number of molecules is the same in the container, the pressure is going to increase. And this is what the ideal gas law is about, that the pressure times the volume is always a constant. And this law is actually called the Boyle's law, when P times V is equal to nRT, and N is the number of moles in the gas, and R is the universal gas constant, and T is the temperature. It's not delta T, it's T, so you have to plug in temperature in Kelvin in the formula when you don't have delta T, so you have to convert in kelvins. So the ideal gas law is defined as one of which all collisions between atoms or molecules are perfectly elastic, and in which there are no intermolecular interactive forces. So the ideal gas law is written, as you can see, like in two different formulas here. It's PV, pressure is P, V is the volume, is equal to N, the number of moles in the gas that we're looking at. R is the gas constant, which is 3.8 joules per mole in Kelvin. So it's a universal gas constant. And the temperature has to be plugged in Kelvin because it's not change of the temperature. So if you move the temperature and divide it by its PV, so if you have PV over T, what you're left is with N and R. So if you take a specific gas, then PV over T is equal to N times R, and it is a constant. So if you take certain amount of moles, and if you change pressure, then the volume or the temperature has to change. And if you change volume, then the pressure or the temperature has to change, because the combination of three of them will always has to give you the same number. It's a constant. And sometimes this law is called Boyle's law, and there is also the same law was stated by Charles, and they sometimes call this law as combined gas law, but in universal name for it would be the ideal gas law. So PV is equal to nRT. Also, if you want to calculate how many number of gas molecules in the gas, then because N stands for moles, so N is the number of moles, and 1 mole is defined as exactly 6.022 10 to the 23rd particles, and in other words it's called the Avogadro's number. So Avogadro's number is how many moles there are, how many number of gas molecules are in 1 mole. So N is equal to the number of gas molecules divided by Avogadro's number. And Avogadro's number, like when you buy eggs, they say dozen, because dozen means there are 12 eggs. And in chemistry or physics, when they say Avogadro's number, that means there are 6.02 10 to the 23rd particles. So that is what Avogadro number is, atoms in 1 mole. So a mole, or how many moles you have to take how many particles you actually have, divide by how many particles in one mole, and that will give you how many moles of gas you have. You also can calculate the number of moles by dividing the mass of the gas that you have by the molecular mass of the gas. So that's how much mass of one molecule would be. So if you know how much gas you have, mass of the gas, and you know how much one molecule of the gas of that gas is, you can calculate the number of moles, because that will give you exact number of moles per mass of the gas that you're looking at. Because this law was formulated at different times with different scientists, some of them wrote it different ways. So some wrote as PV over T is equal to, and instead of N, the number of moles, they would write N over NA. So the number of molecules per gas, per how many molecules in one mole, and then you would have times R. But R over NA, so another important thing to remember, that R divided by NA is actually the Boltzmann constant. So this Boltzmann constant can be replaced, and you could rewrite this same formula, PV over T is equal to as N times K, where N is the number of molecules in the gas and K is the Boltzmann constant. And this constant is equal to 1.4 10 to the negative 23 joules per Kelvin. So because PV over T for specific setting of the gas at certain number of moles is a constant, you can rewrite the gas law as the ideal gas equation. So you can say that the pressure initial times the volume initial over the temperature initial is equal to the new pressure, they called it P2, the new volume, and the new temperature. So because it's always a constant, and no molecules or moles of gas were added into the system, in the system stayed unchanged, the only parameters that were changed, volume, pressure, or temperature, then you can rewrite again the ideal gas law as ideal gas equation, where P1 V1 over T1 is equal to P2 V2 over T2. So let's look at how we can use these formulas to solve our problem. So suppose you are measuring a volume of 1 meter cubic filled with 600 moles of helium, which is very close to an ideal gas at room temperature, 27 degrees Celsius. So that's good to remember, 27 degrees Celsius room temperature. What would be the pressure of the gas? And when we say ideal gas, we have to remember what those rules are or conditions for ideal gas would be. So ideal gas is one where the volume of the molecules is insignificant when compared to the volume of its container. All collisions are elastic. That means that kinetic energy is conserved and no energy is lost during the collisions. And no forces of attraction exist between the molecules. So these are the conditions for the ideal gas. The molecules are too small compared to the size of the container. All the collisions are elastic, so you can use kinetic energy conservation, and no forces of attraction exist between the molecules. So let's set up this question that we just read before. I can write that PV is equal to nRT, and the pressure, they ask you what the pressure is equal to nRT divided by the volume. So the pressure is going to be equal to, if I plug in all the numbers, so I have 600, 8.3 for universal gas constant, and 300 for the temperature. I have to convert it into Kelvin. So the temperature is given in Celsius, and I know that 0 Kelvin is negative 273 Celsius, or 0 Celsius, degrees Celsius, is 273 Kelvin. So because it's 27 degrees Celsius, I add to both sides 27 and I get 300 Kelvin. So I know that the pressure under these conditions is equal to 1.49 atmospheric pressure. And atmospheric pressure from the previous videos, if you remember, that means 10 to the 5th. So it's 1.49 10 to the 5th Pascal. In the next question, they say an ideal gas at 20 degrees Celsius and the pressure of 1.5 10 to the 5th Pascal is in a container having a volume of 1 liter, which is good to remember, it's 10 to the negative 3 meter cubic. And the volume always has to be measured in meter cubic when you plug in into the formulas, the same as temperature in Kelvin. Determine the number of moles of gas in a container, and then the gas pushes against the piston, expanding to twice its original volume, while the pressure falls to atmospheric. Find the final temperature. So again, I can set up that P initial, V initial is equal to nRT initial, and from here I can calculate that N is equal to 1.5 10 to the second, that's PV, and divide by the volume is 10 to the negative 3, and the pressure is 1.5 10 to the 5th, so together will give me 1.5 to the second, and divide by R, which is 8.3, and T, I have to convert 20 degrees Celsius to Kelvin, so I have to add 273 to 20, which just gives me 293. So every time I have T, I have to plug in kelvins, so 293, and that will give me the number of moles is 6.168 10 to the negative 2 moles. And then I can use the ideal gas equation, which is P sub 0 V sub 0 over T sub 0 is equal to P nu V nu T nu. And if we plug in all the data that is given, then I have the new temperature, find the final temperature, is equal to the new pressure, the new volume, initial temperature divided by initial pressure and initial volume. So T is equal to it's going to be 2 times 10 to the 5th and times 10 to the negative 3, and then times 293 for the temperature, and divide by 1.5 10 to the 5th and 10 to the negative 3. So the new temperature is 390.67 Kelvin. And if you want to see what number it would be in Celsius, you just subtract 273 from 390. Here's the next question where they say, suppose the temperature of 4.5 liters, which is 4.5 10 to the negative 3 meter cubic of ideal gas, drops from 375 Kelvin to 275 Kelvin. If the volume remains constant and the initial pressure is atmospheric pressure, find the final pressure and the number of moles in the gas. So to find the final pressure, again, I'm going to use the ideal gas equation. So I have P1 V1 over T1 is equal to P2 V2 over T2. If I'm solving for P2, I have P2 is equal to P1 V1, I do cross multiplication and then I divide by V2, and T2 divided by T1 and V2. If I plug in all the numbers, I get pressure 2 is equal to, maybe I'll do that by steps. If I plug in into my equation, this one, I will have 1 10 to the 5th plus atmospheric pressure, 375, and the initial volume is V1, and that is equal to P2, and I have the volume, but initial and the final volume constant, volume stayed constant, so I can just cancel the volume, and then I divide by, or I could cancel the volume over here in my equation, and I divide by 275, so that's the temperature that the initial one, and the final one. And then so from here I can calculate that P2 is equal to 0.73 10 to the 5th Pascal, or 0.73 atmospheric pressure. And for the second part, they ask you to find the number of moles. So you could do again P1 V1 is equal to ANR T1, use this equation, and then from here you have that N is equal to 1 10 to the 5th atmospheric pressure times the volume, which is 4.5 10 to the -3, that didn't change, stayed constant, divided by R, which is 8.3, and by initial temperature, which is 375. So that gives me the number of moles in this gas is 0.1446 moles. For the next question, they say that 2.1 mole sample of helium gas, initially at 27 degrees Celsius, which is 300 degrees Kelvin or 300 Kelvin, and 0.4 atmospheric pressure, is compressed isothermally. A good word to know. Isothermally means at a constant temperature to 2 atmospheric pressure, 2 10 to the 5th Pascal. Note that the helium behaves as an ideal gas. Find the final volume of the gas. So again, if I set up the ideal gas equation, I have P1 V1 over T1 is equal to P2 V2 over T2. It is at the constant temperature, so temperature can be cancelled, and I have all that is actually equals to N, R, and T, and it doesn't matter because temperature is the same for both sides. So I can find that the volume 1 is equal to nRT divided by P1. So I get 2.1, 8.3, and 300. And all of that divided by 0.4, 10 to the 5th. So that will give me the volume 1 equals to 0.13 meter cubic. And now when I know the volume 1, I can find the volume 2 from volume 2 is equal to P1 V1 divided by P2. So P1, that is 0.4 atmospheric pressure, 0.4 10 to the 5th. V1, we just calculated 0.13, and divided by P2, which is 2 atmospheric pressure, so 2 10 to the 5th, and that will give me 0.026 meter cubic. In this question, we have a beachcomber finds a corked bottle containing a message. The air in the bottle is at atmospheric pressure and the temperature of 30 degrees Celsius. The cork has a cross-sectional area of 2.3 centimeters squared, 10 to -4 meters squared. The beachcomber places the bottle over a fire, figuring the increased pressure will push out the cork. At a temperature of 99 degrees Celsius, the cork is ejected from the bottle. What was the pressure in the bottle just before the cork left it? And then what force of friction held the cork in place? Neglect any change in volume of the bottle. So I have the force is equal to pressure times the area, or air pressure is equal to force over the area. So I can use that, but at first I need to know the pressure. So I have P1 V1 over T1 is equal to P2 V2 over T2. And because the volume stayed the same when the other parameters changed, I can cancel the volume. And I get that if I plug in my numbers, I get P2 is equal to 1.23 atmospheric pressure. And then if I know the pressure, I can find the force. The friction force, is equal to the change between the atmospheric pressure and inside of the bottle. So it's 1.23 minus 1 atmospheric pressure, so that's 10 to the 5th. And times the area, and the area they give you 2.3, 10 to the negative 4. So the force is equal to 5.29 newtons. And if somebody is confused why I subtracted two pressures, so if I have the bottle and there is a cork, then the pressures that the cork is experiencing is, the one is the atmospheric pressure, and the other one is the pressure from the bottle, which is pressure 2. So the actual pressure that the bottle is going through, the cork is going through, it's the difference of these two pressures. And because it's atmospheric pressure, or 1.23 atmospheric pressure minus 1 atmospheric pressure, and atmospheric means 10 to the 5th, so my force is equal to 5.29 newtons. In this question, they say that the tire contains air at the gauge pressure of 510 to the 4th Pascal and at the temperature of 30 degrees Celsius. And the gauge pressure is the difference between the total pressure or absolute pressure and the atmospheric pressure. In other words, the gauge pressure is the pressure that is measured relative to the atmospheric pressure. And the formula for the gauge pressure is going to be the pressure, the absolute pressure or the total pressure, minus the atmospheric pressure. So this is how we calculate the gauge pressure. So again, I can use the gas equation, which is P1 V1 over T1 is equal to P2 V2 over T2. And because they state that the volume of the tire is unchanged, I can cancel the volume from both sides of the formula. And the state at which the volume is not changed is called isovolumetric or isochoric. So if you ever hear the word isovolumetric or isochoric, that means the volume stays the same. Because the gauge pressure is 510 to the 4th, so this is 0.510 to the 5th and equals to the total pressure or pressure inside of the tire minus the atmospheric pressure. And atmospheric pressure is 10 to the 5th. So this is 110 to the 5th. So the total pressure, the one that I have to plug in into my formula, the pressure inside of the tire, is actually 1.5 10 to the 5th. And then I have to change the temperature from 30 degrees, which is 303 Kelvin, so into kelvins. And then I'm looking for the pressure in the tire after the temperature drops, and the temperature goes from 30 degrees Celsius to negative 10 degrees Celsius. So the temperature drops by 40 degrees. So if my initial temperature is 303, if I subtract 40 degrees from here, the new temperature is going to be 263. And from here, I can calculate that the new pressure is equal to 1.310 to the 5th Pascal. But that is the absolute pressure, so that is the actual pressure inside of the tires. But the gauge pressure is the difference between the absolute pressure and the outside pressure, the atmospheric pressure. So the new gauge pressure, is going to be 0.310 to the 5th Pascal. In this question, and I will let you read this question on your own, and then we're going to talk about what is given and what we have to calculate. So the balloon and the iron block need to be submerged underneath the water. So here I have the balloon and the iron block underneath the water. And the forces acting on the balloon and the iron block, we have two masses, mass of the air inside of the balloon plus the mass of the block, and the buoyancy force, buoyancy forces acting up. At first I'm going to calculate the mass of the balloon. So the mass of the balloon is going to be equal to the volume of the balloon times the density of the air, and I get 0.645 kilogram. So the weight of the balloon itself is 6.45 newtons. I can also calculate the volume of the iron. So that is the mass of the iron by the density of the iron, which is 250 divided by the density of the iron, which is 7.86 10 to the third, and that will give me 0.0318 meter cubic. So I know the volume of the iron. And then I have the Newton's second law. For equilibrium, we have B1 plus B2 pointing up minus M1G minus M2G is equal to 0. Or I can use the weights of the balloon and the block to the other side. And what I will get is the density of the balloon is the weight of the water that's being displaced by the balloon, which is the density of the water times G times the volume of the balloon. And then we have the density of the water times G times the volume of the iron. And from here I'm going to be able to calculate the volume of the balloon, and I get 0.218845 meter cubic. Now I can use the ideal gas equation to calculate the final pressure in the balloon. And because they say that the temperature stays the same even at that level of water, so we can cancel the temperature, and we have the final pressure is equal to 10 to the 5th times 0.5 divided by 0.2188, which gives me the final pressure of 2.285 atmospheric pressure. And so that finds the pressure of the balloon at that point. And then the problem that they said that the initial pressure was 1 atmospheric, and then the initial volume was 0.5 meter cubic. So I could plug into my equation, and I found the final volume of the balloon, and that would be this number. And I used it to calculate the pressure in the balloon at that height. And then the last one, assume constant temperature. They already said temperature, that's why I canceled the temperatures here. To what minimum depth must the balloon be dragged? So the pressure inside of the balloon, maybe I will choose a different color. The pressure inside of the balloon is equal to 2.285 atmospheric pressure, and that is equal to rho GH, and this is the height at which the balloon is located, and rho is the density of the water. So I have H is equal to the pressure inside of the balloon consists two pressures. It's atmospheric pressure and the one that is related to the height. So it's actually 2.285 minus 1, because atmospheric pressure we don't count, we only want to know the pressure caused by the water, and all of that divided by the density of the water times G. So I get that the height is equal to 12.85 meters. And this will conclude our video 2 on heat, and it was more so introduction to ideal gas and gas laws. And I will say thank you for watching this video, and I'll see you in the next one.